For anyone who didn't catch my first video, I'm Konstantinos, and I'm building an open source robot arm. In that video, I covered the current state of the robotics industry, as well as some of the basics about the robot arm I'm building. And in this video, I'm going to be diving into the details. If you did watch my first video, this one's going to be a lot more technical. So if you're just here because you thought that one was funny, I'm sorry. Let's get to work. So we know what we want our robot arm to do, but we don't know how it's going to do it, or what it's going to look like. Although I have some guesses about some parts of the system and others I can figure out with math, there's still plenty of stuff that is either really hard to figure out with math, or we just don't know. So we'll make a list of things we know, and also things we have to test. Most individual decisions we have to make can be put into one of these three categories: mechanical, electrical, or software. We'll start with mechanical design because that'll tell us what everything looks like and also how much space we have to work with. Let's take a look at some robot arms. Although these two look a bit different, there's an important part of their design they have in common. Both have 6 degrees of freedom, which means that they have 6 independent joints. To make this a bit easier to explain, I threw together this 3D model. Each section is uniquely colored, and it can only rotate around one axis relative to the section before it. Here's how each joint moves. So we know that our arm will have 6 degrees of freedom. We'll be using the standard layout for those axes so that the base will have 2, the elbow will have 1, and then we'll have 3 at the end by the wrist. Each degree of freedom is moved by an actuator. An actuator is just a device that converts electricity into motion. In the case of robots, that's usually in the form of a motor with a gearbox attached, as well as the electronics to control the motor. This is what an all-in-one actuator looks like. It's a small package that has a motor that's the outer ring, a gearbox within the motor, as well as a circuit board that senses the angle of the motor. This specific one is from an MIT master's thesis, but now there's similar ones available off the shelf. Although these actuators are cool, we won't be using an off-the-shelf actuator because they don't fit the scope of this project. They're not easily repairable and their designs are not open source. On top of that, although they're cheaper than some industrial options, they're actually not as affordable as what we're going to do. Since we're not using an all-in-one actuator, for each joint we'll have to pick out a motor, a gearbox, and the electronics individually. Let's start with the gearbox. Gearboxes allow you to trade a motor's rotational speed for torque. This is important because for the amount of torque required by a robot arm joint, you'd need a massive motor if you wanted to completely get rid of the gearbox. If you did have a joint that didn't use any gearing, that would be called a direct drive joint. This can be expressed as a system with a 1-to-1 gearing ratio, meaning that one motor rotation will result in one rotation of the joint. On the other end, if you had a smaller motor that can spin faster but produce less torque, which is how traditional robots and some cobots work, you would use something like a 100-to-1 gearbox ratio, meaning that the motor would rotate 100 times for the joint to rotate once. This is considered a high gear ratio. This is good for applications that can handle high loads, but higher gearing doesn't come for free. Higher ratios mean more friction and less efficiency. Because the motor has to rotate so fast, these setups also have a very high inertia, which means that they have to be bolted down to a super stiff base. And also, when they're in motion, they take a lot of energy to stop. These aren't big problems in industrial settings, but they're part of what makes high-ratio robots dangerous around people. We will be using a quasi-direct drive configuration. Quasi-direct drive is engineering jargon for sort of direct drive, and it's considered to be a gearbox reduction of about 20-to-1 or less. Practically, it's any ratio low enough so that the joint is easily backdrivable and has low enough friction that it behaves mostly like a direct drive joint. Knowing that we're targeting a reduction of about 20-to-1 helps us figure out how much torque each motor has to produce. Although there's many types of gearboxes, planetary gearboxes like these ones are the most widely available. They come in standard sizes and also they're really well understood. So gearboxes like these, as well as timing belts like these ones that are really common in 3D printers, are what we're going to be using. Planetary gearboxes are named that because the configuration of the gears vaguely resembles a planetary system. Here's one taken apart to show what I'm talking about. The red shaft is the input, which is connected to a small gear in the center of the gearbox. That's called the sun gear. That sun gear drives these 3 gears called the planet gears, and the planet gears are also meshing with the teeth on the case of the gearbox. That outer part is referred to as a ring gear. The plate sitting behind the planet gears is connected to the output, but in this gearbox, the part shown here is just the first stage. And if we take apart the output side, you'll see that the output plate from the first stage is actually driving the sun gear of a second stage. Planetary gearbox stages can be stacked like this to get higher ratios. For example, this gearbox has a 5:1 stage and then a 4:1 stage for a total reduction of 20:1. You may have seen a simple animation like this explaining how a motor works. I won't go into the details, but the important thing to note is that every motor has two parts: the rotor and the stator. An easy way to remember the difference is that the rotor is the part that rotates, and the stator is the part that's static. Motors come in two flavors depending on the arrangement of the stator and the rotor. If the rotor is on the inside, it's called an in-runner motor. If the rotor is on the outside, it's called an outrunner motor. In-runner motors are optimal for high speeds and low torque, and outrunner motors are optimized for low speeds and high torque, which is great for us because they require less gearing. Outrunner motors are very common in drones, and because of that they've gotten very cheap. Specifically, these are outrunner brushless DC motors. The problem is manufacturers don't specify how much torque they produce because that's not as relevant when they're used in drones. So we'll have to do some testing to figure out what size is right for each joint. Because we're using low gear ratios, the friction in the gearbox won't be enough to hold up the arm if there's a loss of power. If we want the arm to stop moving when it's powered off, we'll have to add a dedicated braking system. These electromagnetic brakes act like any other brakes, but instead they work with an electromagnet. So this part here is an electromagnet, and when power is off, it won't rotate. It's actively braking. As soon as we turn the power on, the brake is released, and the rotor is free to rotate. This means that for a robot, if suddenly it loses power, this is a really simple way to make it fail-safe. So power is lost, the brake is activated. For the structure, I'll be using laser-cut aluminum sheets sandwiched with standoffs. This configuration is very light and rigid, and significantly cheaper than CNC machined metal. I can maybe go with a composite like fiberglass or carbon fiber, but that would be way more difficult to work with, and also the aluminum is going to act as a heatsink for the motors. If I was a robot, and my arm was a robot arm, my hand would no longer be referred to as a hand. It would be called an end effector. This is an important term, but basically it just means thing at the end. In most robot arms, the end effector is swappable, so it could be a basic gripper or a welder or literally anything else. There's standard sizes for these end effector mounts that are easy to say, like ISO 9409-1-50-4-M6, which happens to be the one I'll be using. For this project, I'm going to make a basic gripper eventually. Earlier we looked at a simplified explanation for an actuator, so let's look at it in more detail. We'll start with the motor controller, which has a very important job. We said that it takes electricity and a signal, some magic happens, and then we get torque out of the gearbox, but to be more specific, ours will take in 24 volts, and the signal is more like a constant stream of commands for the target output position and torque. And the controller sends back telemetry, like motor, power consumption, temperature, and a lot more. The controller then uses this data to correctly sequence power to all these little electromagnetic coils in the motor to push and pull on each magnet with the right force at the right time. At the same time, it reads the angle of the rotor super precisely to verify how far off the target position it is with a chip that's called a magnetic encoder. The encoder senses the angle of a separate little magnet that's attached to the rotor for this purpose. Here's an example setup to show what I'm talking about. The shaft I'm rotating with my hand has a small magnet at the end that's read by the encoder that's on the circuit board. On the left is a live plot of the angle of that magnet. The motor controller also measures the current going through all of the motor windings to calculate how much torque the motor is producing. And it has to do these things very quickly, about 30,000 times a second quickly. The process I just described is called Field-Oriented Control, or FOC. And a company called MJBots has a line of fully open source FOC controllers that I've used extensively in other projects, and I've even made my own custom controllers based off of theirs. For now, I'm going to use these motor controllers directly while I figure out the rest of the system, and in a few videos I'll be designing my own custom ones. These motor controllers by default use a CAN interface to communicate, which is a high-speed protocol that was popular in cars and very resistant to electromagnetic noise. CAN only requires 3 wires and can be daisy-chained, which is going to make harnessing for the arm super simple. For the main controller, for now I'll stick with a Raspberry Pi, because I have a few lying around, and there's also an MJBots Pi hat that's compatible with it, but I'll be exploring more options down the road. The software running on the main computer will have to do a few things. Since each motor controller is only worried about the joint it's connected to, the main computer is responsible for coordinating the different joints with each other. When I'm using the robot arm, I usually won't care about what's going on with each joint, but rather what's going on with the end effector. If I use the angle of each joint, plus some high school geometry, I can figure out the exact position of the end effector relative to the robot base. This math is called forward kinematics. If instead I want to tell the robot to move its end effector to a specific position, and it has to figure out how to pose each joint to get there, that math is called inverse kinematics. The software running on the main computer has to be able to perform this kind of math. It should also be able to tell me how much force is being applied at the end effector, as well as digesting all of the data coming from the robot to make sure everything is safe, such as motor temperature, collision detection, and diagnostics. There's an open source library called ROS that can help with a lot of the tasks I mentioned, so to get started I'm going to be using ROS and also writing any software required to fill the gaps. So to recap, here are the decisions that I've made so far, and here are the things that we have to find out with testing. The highest priority item on the list is motor testing, since that's going to have the biggest impact on other items on the list. So next video is going to be all about that. See you in 2 weeks!